In this video, we are going to go over another algorithm for computing the minimum spanning tree. This algorithm is called Kruskal's algorithm, and in the previous video, we discussed what is a minimum spanning tree. So, just to reiterate, a minimum spanning tree is a subset of the graph that contains all the vertices which were there in the graph, which are connected by exactly one edge. So, let's see a worked example of how Kruskal's work, and then we are going to see some implication peculiarities that are specific to Kruskal's algorithm. So the algorithm takes in a directed and undirected weighted graph, and it returns a minimum spanning tree. So how this works is, first you are going to sort all the edges or the edge weights in the order of ascending edge weights. So you can see that the edge 0 to 2 has the least weight and 2 to 4 has the highest weight. Now, since all these weights are unique, we'll have just one unique minimum spanning tree. But let's say if these edges had some weight that was non-unique, which is like instead of 5 6 there were two edges with 5, then this algorithm can have multiple minimum spanning trees depending on its implementation. So how this works is, we are going to create a new tree from our original graph such that there are no cycles. So we keep on adding edges to this new tree unless it creates a new cycle. So in this case, we start with 0, 2. Since the weight is 1 and our graph is right now, our minimum spanning tree is completely empty. So we are going to add both 0 and 2 and with weight 1. So that means in our final minimum spanning tree, this edge is for sure going to be there. Next, we pick the next smallest edge, which is 3, 5. Now, since 3, 5 is also like, if we add 3, 5 to our minimum spanning tree, it's not going to create a cycle because it's still a separate component. And in fact, this type of structure is called disconnected components in the form of a graph. So in this case, 0, 2 and 3, 5 will be selected in as a part of the minimum spanning tree because they don't create a cycle. Next, we have the 0, 3 edge. So again, like if we see the graph, 0, 3 is not going to create a cycle. So we are also going to keep this. Next, we have 1, 2. So in this case, 1, 2, if we mark this edge, again, you can see this is not creating any cycle in our new MST. So we are going to keep this as well. Next, we have 2, 3. So 2, 3 will now create a cycle, which is like this is a cycle. So we are not going to choose this 2, 3 edge. As you can see, then you have 2, 5. So 2, 5 will create a cycle because you have a cycle right here. So we are again not going to use this as a part of our MST algorithm. Again, like the last one, the next one is 0, 1. So in this case, 0, 1 is again creating a cycle because we have a cycle right here. And in this case, we are not going to use 0, 1 as well. Next, we have 1, 4. So in case of 1, 4, there will not be a cycle because you see the 1 and 4 is not connected, or 2 and 4 is not connected. So we are going to keep 1, 4. Next, we have 4, 5. So 4, 5 will create a cycle because we then will have this entire graph as a cycle. So we are not going to keep 4, 5. And finally, we have like 2, 4. So since 2, 4, like if we add this edge 2, 4, it's again going to create a cycle. So we are not going to add 2, 4. And at this point, we stop. Like there are other ways to stop this algorithm as well, which is once we have processed each of these nodes or each of these edges, we can push them in a visited set. So when the size of the set is equal to the number of vertices in the graph, we can stop right there because we know that we have already connected all the vertices. Another way to look at this is you can we know that if we have a minimum spanning tree with or a graph with v vertices, the minimum spanning tree will have v minus 1 edges because each of the vertex is connected to one edge. So in this case, we can also stop when we have already added, like in this case, there were 6 different vertices. So we can stop when we have just like 5 edges that are added. So we can see like 1, 2, 3, 4, and 5. So at that point, we can stop. And we know like automatically 2 and 4 and 4 and 5 are not going to be there in our final minimum spanning tree. So a lot of questions might be asking you what is the total sum of the minimum spanning tree. So in this case, like what is the cost to traverse the entire minimum spanning tree? So you are just going to sum up all the green weights. So in this case, it will be 4 and 3, 7, 9, 10, and 18. Now, I think we are going to have another video on like how to implement this. So I'm going to stop this video right here, and then we are going to discuss like how we actually implement this.